Right. Good afternoon. Welcome back. Any questions? Any comments? All right. Let's recap what we did last time. So what we said last time was our second example to understand the quantum mechanics was harmonic oscillator, and harmonic oscillator is this 1/2 kx squared potential is utilized in the Schrödinger equation. So we write the Schrödinger equation and we said our job is to solve the Schrödinger equation. And the solve means we need to find the wave functions, all possible solutions, and corresponding energies. And what we said is like any object in the form of u squared plus v squared can be decomposed into product form. Like something like minus iu plus v times plus iu plus v. Good. And with that motivation, we defined a plus and a minus. And a plus and a minus, we have to remember these are operators. But we said we are adults, we agreed what operator is and what operator is not. I know P is an operator, I know A is an operator. I don't have to go around and put head every time. Okay, that was our commitment. And if you forget, I can put heads, no problem. And since these are operators, the way they act is important. Their ordering is important. For that, I wanted to calculate A plus and A minus, and I had a factor like this. To see this factor, I considered Px, and I found that Px is actually not Xp in quantum mechanics, right? Some people think that's the most fundamental thing about quantum mechanics. Two things, if you change the order, are not the same thing. But in classical physics, Px and Xp, they are the same thing, right? We cannot distinguish these two. And a compact way to represent this this result is so-called canonical commutation relation. And canonical commutation of any two operator AB is written as AP minus BA. And for X and P, in like a little bit of two-line calculation with like a test function, we found that commutation of X with P is IH bar. Later we went back and we wrote A plus A minus in terms of commutation of X and P. And then we found that A plus A minus gave us exactly the Hamiltonian up to this constant term. Then we wrote the Hamiltonian in the form h bar omega A plus A minus A plus minus a half. So we just rewrote the Hamiltonian. We didn't do anything. Later, we said A and A minus and A plus, they include factors of X and P do not commute. So we need to get used to this language because sometimes an efficient way of saying something is good so that you don't get confused. When they say they don't commute, the order matters, right? If X and P order matters, if they don't commute, A minus and A plus also don't commute. Or should they commute? And here we checked that. We wrote A plus A minus A plus. We cancelled what can be cancelled. And at the end, we found A minus A plus commutation was equal to 1. We also called this canonical commutation relation for A minus and A plus. And at the end, using the commutation relation, right, whenever I see A minus A plus, I can use the commutation relation. A minus A plus A minus is equal to 1. Then whenever I see A minus A plus, I can write 1 plus A plus. I change the order, then add 1. So that's the rule. Here I changed the order and add 1. And I wrote the same Hamiltonian, A plus A minus. This is plus minus, this is minus plus. Basically, if you want, we change the variables, right? And then afterwards, we change the Hamiltonian from Px to A minus A plus. You want me to go up here? So this, for example, in the box is exactly the same Hamiltonian. This is also equal to, so this is not a new thing. The same thing written in a different form. Minus h bar squared over 2m d squared dx squared plus 1/2 m omega squared x squared. Right? And our job is to understand what this Hamiltonian object does on functions. Good? So there are two representations. H is equal to h bar omega a minus a plus or a plus a minus. If this is minus plus, this is minus. So we have to learn to be careful about these little things. And if this is plus minus, this is plus. And you can, given this one, you can easily obtain this one using commutation relations. And vice versa. Okay, so now I think I want to run this whole calculation one more time. Let me copy here and then repeat this line. So let me take this. Actually, let me take this whole thing. And do the last thing we did one more time from scratch. Now is the question. Now is the hit. Suppose we said. Suppose psi is given to us. Somebody gave us a solution psi with E is given. A solution. And what is the meaning of this? The meaning of this, H times psi is equal to E times psi. That's exactly what that sentence means. This is our starting point now. And we know what H is. H is h bar omega a plus a minus plus a half. Right? This thing is an operator. I don't need to write it because we talk about it. And it is hitting on a function psi. This complicated thing just spits out just a number E psi. That's the meaning of that given sentence. And in the second step, we say, okay, this is the given solution to us. Let's try something else. And I call this psi tilde. So this is my definition. Now I introduce something new. And this new thing is a dagger acting on this initially given psi. Okay? Initially given psi. I take it, hit on it with an A plus. And I wonder if I act on this psi tilde with H, what am I going to find? Right? And that's the task. So now let's try to do this. So we want to calculate H psi tilde, which is equal to, let's write H first, H bar omega. This is A plus, A minus, plus a half. Now I wrote H. Now I'm going to write psi tilde. Psi tilde is A plus psi. Now I want to put this A plus inside. So what do I want to do? I want to act this H on psi because I know what it does. Because if this thing in the circle, I can hit it on psi with it, I know it's very simple. It's just going to give me a number E, and a number can just move around. So it's not an operator. It's very simple to work with numbers. That's my goal. And to do that, first, let me, right, this is a parenthesis. I'll just put this A plus inside first. This is A plus. So this is A plus. Since I pushed it inside, I can erase this. No order changed, no nothing changed, right? I just changed the parentheses, that's all. Now this A plus, and this is also A plus, I can now take it on the other side. So let's also do it in 2 steps. So I'll take this piece outside and write what's left to the right hand side. But since I wrote this and this, that's gone. Now I look at this. This is almost Hamiltonian, but not, right? Hamiltonian I started with was plus minus plus a half. This is minus plus plus a half. So I want to turn it to Hamiltonian. And it's also very easy, right? The commutation relation was what? A minus, A plus was 1. That means A minus, A plus minus, A plus, A minus is 1. That means whenever I see A minus, A plus, let me write one more line. I can write it is equal to A plus, A minus, plus 1. Is that clear? So then here I'm going to write, so this thing, A plus, A minus, plus 1. Now this line, let's write one more time. So this thing is maybe a little bit lower. So the first A plus, h bar omega. Now this one is A plus, A minus. This thing I wrote. Let me write 1/2 first. 1/2. This thing I wrote. And there is h bar omega. And this h bar omega, I want to write it separately. Plus h bar omega. And write it like a parenthesis like this. If you want, I'm like rearranging the parentheses to get what I want. And at the end, there's like psi. Good? Any questions? But now this is exactly h. So this thing is exactly the h I started with. This thing is just a number. And h is hitting on psi. If I hit on psi with h, what do I get? Energy, which is a number. Then let's also write that. So this is A plus E plus h bar omega psi. Now, this E is a number, right? H bar omega is a number. This entire thing is a number. And numbers can just go around. So in the last step, I can just be real pedantic and rearrange it like this. And this thing, as you can see, was my psi tilde. So I go to the beginning of the calculation. I have h psi tilde is equal to E plus h bar omega psi tilde. Right? So h psi tilde is equal to E plus h bar omega psi tilde. Therefore, we just proved A plus psi is also solution, but with energy E plus h bar omega. Good? Yes?
We introduced the h star tilde as a negative sign.
Yes. So initial this psi tilde I introduced like this. This one you are asking, right? Yes. Yeah, I shouldn't say A dagger. I think because I use A dagger. Whenever I say A dagger, I think it's A plus. I apologize. That's no, it is not. It is it's like a habit. I meant to say A plus. I'll be a little bit more careful. Thanks for pointing that out. So then A plus psi is a solution with h bar E plus h bar omega. Similarly, you can do exactly the same exercise. No, nothing new is included. The same calculation, but being careful with the pluses and minuses. A minus times psi is also solution with, that's the difference, E minus h bar omega. Good. Now the technology, we changed the variables to A minus and A plus, and this new technology enabled us to not solve anything yet. But if anyone gives you one solution, you can, in principle, generate infinitely many solutions by hitting with A plus and an A minus. Yes?
Change anything if we use the other harmonic, which is the same information, like the A minus.
Yeah, exactly. Here's your exercise. If you show this, using the other Hamiltonian. If you use plus minus, it's much harder. I mean, like pluses and minuses, it's like their order is important. It's just simpler to use this form. H bar omega, A minus, A plus, minus a half. You can also use the form we use, but you need to commit a little bit more. Yes? Like for the moment, everything is operational. Like what A does is, so here's what A does. Somebody gives you the solution. Let's call this psi with E, and you hit with A plus, and this A is going to generate, let me write it like this. You hit with A plus, and it generates another solution, E plus h bar omega. And you hit with A minus, it generates another solution, E minus h bar omega. So that's why this kind of looks like a ladder, like this is like a ladder. And these things are called ladder operators. That's all physics it has, right? There is not more than anything more than that. And also more terminology. A plus is called raising operator, and A minus is lowering operator. Good. And you can generate all solutions with these operators. Yes.
A minus this many times, that means we can go always over energy.
Yes. Now let's come to that. Now this means, okay, thank you. If I hit with A plus, I can in principle generate states with plus infinity energy, right? That's not a problem because we also had like plus infinity in particle in a box. Infinite energy is not a problem. However, if I keep doing this with A minus, at some point, I'm going to go to minus infinity. And before going to minus infinity, at some point, A minus psi, if you keep adding on, like hitting on the wave function, I don't know, more and more, let me write it like this, A minus dot dot dot, A minus is going to give you E is less than 0. And the question is, what's wrong with E less than 0? Are they acceptable? Why not? Is not normalizable. Why?
Does not go as fast as 0.
So it's not normalizable, but why is that? I'm just curious. We had like an exercise a couple of lectures ago, and your exercise was whenever E was less than V min, you were supposed to prove psi was non-normalizable. Yes, but I gave this as an exercise. Yes, exactly. If nobody did that, That's the point for you to, exactly. Like there's like, you have to look at the second derivatives and V min, and if you didn't do it, this is your exercise again, because this will come back again, exercise. Okay? And here in the harmonic oscillator, V min is 0, and for normalizable solutions, you cannot have a negative energy state. Good? But still, if you want optional homework, if you are still having difficulty working with derivatives and like limits, things going to plus or minus infinity, this is very easy, just 5 minutes of thinking. Good? So therefore, we need a new condition to impose, and this new condition is, at some point, A minus should hit a special state, and that special state we are going to call psi 0, and it should give us 0. Okay? Uh-huh. Uh-huh. Two values? Like this one says no, right? Right now we are also coming to that. Suppose there was like a solution between the letters, and you keep hitting with lowering operator, and you went to this state. There is only one state like this, and we are going to solve it in a little bit. Yes. Yes.
That's why there is no other.
Exactly, and there is no other solution. And this state besides 0 is unique, and saying only one state is unique is sufficient for us to say all other solutions are unique. Because you built, if you want, this is going to be our vacuum, and we are going to start from vacuum and build everything else. Yes. Now we want to solve this besides 0, right? That's our task, and I think we have a good time for that. Let's do this. So what was A minus? A minus was 1 over 2 h bar m omega. So A minus is I times P plus m omega x, and this entire thing is acting on psi 0, and this is giving us 0. So that's what we need to solve now. So now this is an overall constant. Let's quickly solve this equation and take a break. So this overall constant I can get rid of, and P is minus I h bar d dx, and minus I plus I, this is like I minus I h bar, let me write it h bar d dx, right? I didn't mess up anything. And I will take this h bar d dx psi 0 is equal to minus m omega x. Let me also write h bar here, h bar, and this h bar is gone. And that's the same equation, right? I can take, okay, this is also psi here. Sorry, I forgot. So this is psi 0. Now I will take this psi 0 to here, this dx to here. This is 1 over psi 0, and this is dx, and it is exactly the same equation. So this is logarithm psi 0 is equal to minus a half m omega over h bar x squared plus a constant, then psi 0 of x, a normalization constant, times e to the minus a half m omega over h bar x squared. Good. And now how many people can normalize this function? Okay, let me do it quickly then. Like normalization. So 1 is equal to dx psi 0 squared. And this is going to be, let me write it. So dx minus infinity plus infinity a squared e to d, they are squares, so it is going to be m omega over h bar x squared. And let me call this alpha, like let's define alpha is equal to m omega over h bar. Yes, minus, thank you. So I define alpha, so this is alpha. So what I will do is I'll put root alpha and divide by root alpha. And this is equal to a squared divided by root alpha minus infinity plus infinity du e to the minus u squared, right? And this thing I remember, this is root pi. Any objections?
Because taking into of a power minus 1 squared is, I think there is not such thing.
Why? I didn't understand. Can you say one more time?
Just because we know that in taking values square root pi, a value calculations.
The way I know this from Gaussian integral. I remember it, but sometimes I forget. I look it up. But if you want, I can show you how to derive it. There's like a nice trick. How many people know how to derive this? Like it is actually not very hard. So the way I was taught, I think there are the different ways. You take 1 and you call this is equal to, I don't know. Let me call this b. You take the square of this. And because this is like a integral, I can change it from u to x, right? That's like a dummy variable. And I can change it from u to y. And this is b squared. Now I can do it like dx, dy, e to the minus x squared plus y squared is r squared. And dx, dy is r, dr, d theta, but d theta is symmetric. This is 2 pi. And this is 2 pi e to the minus r squared over 2, I think, right? And this is from 0 to infinity. And this one is going to give you pi, right? Then b squared is pi, then b is equal to root pi. Good. If you want, you can do one more change of variable here. So let's call it u. This is 1/2 u. Then everything works. Yes. So this is going to be e to the minus. So this is pi e to the minus u. And I think I need also a minus one, right? Yeah. Anyways, at the end it is pi. Once I know that, let me just write that and take a break. So this is a is equal to, let me write the normalized wave function and take a break. So here's the normalized wave function, psi of x is equal to m omega over pi h bar e to the minus 1/2 m omega over h bar x squared. Right? Let's take a break and continue in the second hour.